Let's consider ion forces. One of the simplest examples of this would be, say, sodium chloride, just common table salt. It consists of a sodium atom, which has an electron missing, so it's a sodium plus, and a chlorine atom that has accepted that electron from sodium, so it has a minus charge. So these are complete charges. So sodium has a plus 1 charge, chlorine has a minus 1 charge, and there's an attraction between the sodium and the chlorine because of the attraction of these two charges. There's an electrical force because of the difference in charge. Opposite charges attract, and each charge exhibits an electric field which exerts a force on the other particle. Now, the potential energy between two charges is equal to, and these are constants, 1/4, and we have pi and epsilon naught, which is a constant of nature. But the important parts are the charges of particle 1, the charges of particle 2, divided by their distance. Now the force acting on these particles is equal to the negative derivative of the potential energy with respect to our coordinate, which is r, the distance between the two particles, and that is going to be equal to so again, the force is directly proportional to the magnitude of the charges. That's supposed to be a 2. I don't know how it turned out to be an R. So the higher the charge, Q1 or Q2, the greater the force. Now the force is acting in a negative direction, so it's pulling each particle in toward the other one. Well, you might ask, why don't these particles just keep moving into each other until they bump into each other and collapse into one particle? Well, there are electrons surrounding these sodium and chlorine atoms, and so those electrons will start to repel each other, and those repulsions will overcome the attractive force, and so when those forces balance, the sodium and chlorine atoms will be stationary with respect to each other, so they'll find a balance and find an interatomic distance. That will be the bond length between the sodium and chlorine atoms. So you'll have a sodium chlorine bond length, and that's the length where these attractive and repulsive charges balance. Now, since these are plus 1 and negative 1 ions, Q1 and Q2 are plus E and minus E, and E is the charge on the electron, and therefore ion charges are the strongest because they represent a complete positive or negative charge. Now let's consider Ion-Dipole interactions. Now here we have an ion, say sodium plus, and it's going to interact with a molecule that has a dipole moment. So we need to consider what a dipole is. As its name implies, di meaning two, pole meaning like ends or charges, like you have two poles of a magnet, the north-south pole. You can have two poles for an electric charge, the positive and negative end. So in our case, it will be a plus and a minus side of a molecule. So let's consider a simple dipole. So we'll consider the molecule hydrogen fluoride. So in this molecule, fluorine is much more electronegative. And so it attracts electrons to itself, and so hydrogen and fluorine are sharing 2 electrons to form this chemical bond between them. Well, since fluorine is so electronegative, fluorine actually is attracting the electron that hydrogen donated to this bond more toward itself. So there's an abundance of electrical charge building up around fluorine as opposed to hydrogen. Now, it's not an ion. We do not form H plus and F minus. So it's not a complete transfer of an electron. It's what we call a partial transfer, which means that in a time sense, the electron spends more time closer to fluorine than it does hydrogen. And so fluorine has a partial charge because the electron is spending a little more time near fluorine than its own nucleus hydrogen. And we use the symbol delta to represent partial. So we have a partial negative charge around fluorine and a partial positive charge around the hydrogen. So we would draw this as partial negative on fluorine, partial positive on hydrogen. And again, it's not a complete charge because there's not a complete transfer of electrons. It's just that hydrogen's electron spends a little more time on fluorine than it does closer to hydrogen. This produces a dipole because there are 2 poles or 2 charges, the plus side and the minus side, and it's permanent. This dipole is permanent, meaning that it doesn't change over time. It's spelled permanent, right? I don't spell very well. Permanent. I leave out letters a lot because I think about what I'm going to say next while I'm writing. So we could have an interaction between the sodium plus ion and the HF molecule. So in this case, the fluorine would be closest to the sodium because the fluorine has a partial negative charge. And so there would be attraction between the partial negative charge of fluorine and the plus charge of sodium, since opposite charges attract. If I tried to put the hydrogen close to sodium, they're the same charges, positive and partial positive, and they would repel each other. So this is an example of an ion dipole interaction.